He's a faculty, he's a professor at IISER. So Professor PhD NMRs, I believe, from Professor Anil.
I'm sorry, your voice is breaking. I mean, I can't hear you properly. Maybe it's a problem at my end, but
yeah, the same on my side also. Breaking noise, breaking voice.
so, I mean, should I start? I was kind of waiting for a go ahead from the chair. Or maybe you can just write in the chat.
Yeah, can you hear me now?
Yeah, it's better. Yes.
Yeah, can you hear me?
Yeah, I can hear you. Yes.
Yeah, okay. I'm so sorry. Yeah, there's some issue with the internet here. Yeah. So let me welcome Professor Rangeet Bhattacharyya, who's a professor at IISER, Kolkata. And Professor Bhattacharya did his PhD on NMRs with Professor Anil Kumar at IISC, if I'm correct. And after that, he followed that up with postdocs at Weizmann Institute, Stony Brook University in the US, and also spent time at Southampton University in the UK. Since 2010, he has been a faculty at IISER Kolkata. And as most of you from IISER Kolkata are aware, he is now a full-time professor there. And he has various interests ranging from as NMRs to driven-dissipative systems, among many other things related to quantum computation and quantum technology. And today he is going to be talking to us about the emergence of Born rule in strongly driven dissipative systems. So Professor Bhattacharya, yeah, please take over.
Okay. Oh, thank you. So thank you, Dr. Thar. I mean, it's a very nice introduction. Thank you. And I also thank the QIQT team, Professor Panigrahi, for the invitation. So today I will talk about one of our work, recent work on the emergence of Born rule in a strongly driven dissipative system. So the Born rule, I mean, it is one of the postulates of quantum mechanics. And what it says, I mean, what it describes is, it describes the rules of quantum measurement. It was given by Max Born in 1926. So suppose we have a quantum system. You are familiar with Born rule, but I think I will describe that once more. That suppose we have a quantum system and we would like to measure an observable O. And let's suppose this observable has eigenvalues lambda I and corresponding eigenvectors are phi I. These eigenvalues may or may not be degenerate. Now, suppose we prepare our system in some initial state, psi ini, and that we can write in terms of as a linear superposition of the eigenbasis of the observable. It's our choice. I mean, it's particularly convenient if we do that. Now, if we perform a measurement, then the probability of getting a particular eigenvalue, we always get one particular eigenvalue, and that particular eigenvalue, say lambda I, the probability is mod Ci square, where Ci is the projection of the initial state onto the phi I, the state where the initial state collapses to. So essentially, we prepare an initial state, we make a measurement, the system collapses to one of the eigenstate of the observable, and we measure the corresponding eigenvalue. This is the description. So it was originally proposed as an ad hoc manner, in the sense that it explains experiments. However, these cannot be obtained from other theoretical framework. So for example, the measurement process, it is not unitary the way it is described. So post-measurement description of the system, it has to be done using a mixed state. So for example, say we prepare our system in some initial state and we let it evolve according to Schrodinger equation. And then we know that initial state will move on to some final state. And this description, this is completely reversible unitary dynamics, in the sense if we are aware of the final state and then we set time to we evolve in the other direction, we get back the initial state. So it's a one-to-one mapping between the initial state and the final state. On the other hand, if you look at the measurement, this is much more complex. I mean, we can have some initial state, and after the measurement is over, the system can land up in one of the final state, one of the, let's say it is in phi1, which is the first energy eigenvector of the observable. And the probability would be mod C1 square. C1 is being the complex number, the projection onto phi1. And similarly, a probability of getting there in phi2 would be mod C2 square. So, I mean, because the final ensemble, it is not a pure state. It could be a statistical mixture of phi1, phi2, phi3. A natural description is a mixed state description. So the big question that was always asked, that how does this take place? I mean, do we have any analytical picture? So, I mean, I would like to show you a simple example. I mean, what I mean by measurement, quantum measurement. I mean, suppose we consider a two-level system, a spin-up particle. And let's consider an observable sigma x, Pauli matrix, x direction 0, 1, 1, 0. This is the matrix. And its eigenvalues are plus minus 1. Corresponding eigenvectors phi plus and phi minus are 1 by root 2. Symmetric and antisymmetric combination of 0 and 1. The basis states for sigma z. So if this observable we try to measure, and let us suppose we have some initial state psi initial, which we write in terms of phi plus and phi minus, the basis state, C1 phi plus and C2 phi minus. And so in this basis, the state vector looks simple, C1, C2, just two numbers, two complex numbers. Now, if we perform the measurement sigma x according to quantum mechanics, according to Born rule, what we are supposed to get, the probability that we will have lambda equal to plus 1 is mod C1 square, and the initial state will collapse to phi plus. And the probability mod C2 square would be to have the probability to have the eigenvalue minus 1, and the system will collapse to phi minus. So after the measurement, if we try to look at, if we try to look at the density matrix before and after the measurement, let's look at it before the measurement. The initial density matrix is the product of initial kit and its adjoint, and that gives us mod C1 square and mod C2 square in the diagonal, and in the off diagonal we have C1 C2 star and C1 star C2. It's simple. Now, in the final density matrix, which is even simpler, it just happens that after the measurement is over, the system is either in phi plus or in phi minus with corresponding probability mod C1 square and mod C2 square. So which means that we will have the final density matrix simply diagonal. So this is our initial density matrix, and this is the final one. The question that I would like to ask, our lab, we are asking and we are trying to answer the question that how does this take place? Is there any equation that gives us this dynamics? So far as we know, the Born rule is one of the postulates in quantum mechanics, which means that we take it for granted, we do not derive it. However, there have been many attempts to do that. So ours is one such attempt. We would like to see, how it comes about. This is the talk about. This is the essentially the motivation of the talk. Now, we understand that this question, we are not asking this question for the first time. Originally, the question was asked by von Neumann long back. So what he did is called something like a pre-measurement. So suppose we have a system, psi, and we'd like to measure an observable on this system. We prepare an apparatus, corresponding apparatus. And then we take initially uncoupled system and the apparatus. And von Neumann showed that it is possible to construct a Hamiltonian, which will give us an entangled form, entanglement between every observable eigenstate and a corresponding apparatus eigenstate, which is like a pointer state. So essentially, if we have that, and then suppose we make a measurement on the apparatus, then the apparatus, according to him, it collapses to a particular AI, and the system will collapse to a particular phi I, the observable eigenstate. So this is all fine, but even for von Neumann's case, the mixture has been prepared using an unitary prescription. That means a nicely entangled states between every every eigenvector of the observable and corresponding apparatus state, but still it does not describe the collapse. So the question remains, how do we get from a pure state description to a mixed state description? The first hint into this came from Zurek, and he had a very famous paper in 1981. And he asked the question, then to what mixture does the wave function collapse? And he kind of hinted that it could be the environments playing a big role here, in the sense that system connected to an apparatus, the apparatus is essentially connected to the environment, local environment, which might be undergoing fluctuations. And it is the coupling with the environment which kind of triggers the collapse. So, motivated from Zurek's view, it is clear that if we bring environment into the picture, then we do not use Schrodinger equation anymore. The typical way of describing the evolution of a quantum system, which is coupled to an environment, is by quantum master equation. So if we ask the question, how does the density matrix evolve? We already have seen that it is the density matrix which is the natural choice for the description of the system, not exactly a wave function, because in our case, the evolution is non-unitary. The system is going from pure state to mixed state. So we ask the question, I would like to show, how the density matrix evolve. So we begin with Schrodinger equation. The rate of change of a wave vector, wave function, is given by a prefactor minus I by h cut, and the Hamiltonian acting on the wave function. That's simple. And corresponding von Neumann-Liouville equation is similar. The rate of change of density matrix. Density matrix we construct it by taking an ensemble average of the wave function and its adjoint, as I showed in the example before. And so the rate of change of density matrix is equal to the same prefactor that we had in the Schrodinger equation and a commutator between the Hamiltonian and the density matrix. Now, this equation is actually unitary dynamics. It does not show any non-unitary behavior. So to have the non-unitary dynamics, oftentimes we consider a system which is coupled to an environment. So we take the system coupled to an environment, we let it evolve under the system environment coupling. These entangle system and environment, and then finally we take the trace over environment, and what we get is an equation of motion with the dissipator. So our equation looks slightly different now. That rate of change of density matrix, we have a first order commutator and a dissipator. This dissipator in the Lindblad form, it involves some system operator which are AK and AK dagger, and it has a complex structure. The gamma K, which is a number, complex number, which carries the signature of the environment, and we have a anti-commutator between the density matrix and AK dagger and AK, and with a prefactor hop, and AK rho AK dagger. This is the dissipator. So it is basically quantum mechanical analog of friction. So the entire equation is known as Lindbladian, and it provides what we call relaxation dynamics. So this relaxation is slowly influenced by the system environment coupling. Okay, so it takes the system to equilibrium, and essentially this quantum master equation, it is not connected to Born rule. It has nothing to do with Born rule. If we have a quantum system connected to an environment, the environment has is like a thermal bath. Suppose it is characterized by a certain temperature. Then if you let the system be, you do not apply any drive or just let it relax, it will go to equilibrium and it will inherit the temperature as the thermal bath, just like as it happens in a classical system. And this equation describes that. This is well understood. But what this equation does not capture is this, that suppose we have a quantum system and we apply a drive on the quantum system, meaning external perturbation. For an optic system, it could be laser. For magnetic resonance, it could be a time-dependent magnetic field. Suppose we apply that, then oftentimes we see the drive-induced dissipations taking place, meaning there is a dissipation happening because of the drive. Those are typically not taken into account by the quantum master equation. So can we have a more accurate picture that takes this drive-induced dissipation into account? And we will show that it is possible, but before that, I would like to tell you that the quantum master equation, it looks formidable with all these apparatus and dissipator, but in reality, when we calculate it and final dynamics, it gives us often time for time-independent drive and simple thermal bath for Markovian dynamics. We have a very simple set of equations. We go to Liouville space. Instead of density matrix writing it a matrix form, we write the density matrix elements in a column form, as you see here. In the Liouville space, the equation is simple first order ordinary linear differential equation. So the rate of change of density matrix is we have contribution from the drive in the first order and the system bath coupling in the second order. These are the relaxation terms. So in the matrix that I show you, the coefficient matrix, the highlighted terms are the relaxation term. They ensure that if you let the system be, it goes back to an equilibrium. And in this case, what you see here, it's basically for a simple two-level system. Throughout our talk, we will only talk about simple two-level system. And so our density matrix is 2 by 2. And this two-level system, when it goes back to equilibrium, M0 is the equilibrium polarization. The rate with which the population goes back to equilibrium has a characteristic time, and that is given by T1. And the T2 is the rate with which the coherences decay. And this omega-1 that you see here is the external drive. If we set omega-1 0, then there is no external drive, system relaxes back. But if we do have omega-1 present, and then we have Rabi oscillation taking place in the system. If we set T1 and T2 infinity, then we see Rabi oscillation happening forever. But if we set T1 and T2 finite and with some omega-1, then the Rabi oscillations decay. So this is just a very similar situation as an underdamped oscillation, underdamped oscillator. So here, this equation, it may not look familiar to us, but if we rewrite it in terms of the expectation value of the spin observables, then what we get is a set of block equation. This we know. The block equation describes how simple magnetization going back to equilibrium. So this is the quantum master equation, how it looks like operationally. Of course, calculation of T1 and T2, those are still formidable tasks. Now, as I mentioned before, that we would like to rederive quantum master equation in a way that it should give us the drive-induced dissipation. To do that, we take a slightly different route. What we do is this. We take a quantum system, connect it to a thermal bath, and we assume this thermal bath is also a quantum system. It has energy eigenvalues. And this energy eigenstates, the energy eigenvalues are fluctuating. Those are the fluctuations in the local environment. And because the bath energy eigenvalues are fluctuating, the bath coherences, they decay exponentially with a characteristic time tau c. So typically, for a quantum system connected to a bath, we have multiple time scale. Bath has fluctuation, and as a result of the fluctuation, bath correlations decay. They decay pretty fast. On the other hand, the system evolves rather slowly. If it does, in such cases, we are trying to derive this equation. I mean, there could be other possibilities where the system is equally evolving very fast. In such cases, we cannot use a quantum master equation. Or in other words, the system is not exactly Markovian. For Markovian setup, we must have a good time scale separation between the bath dynamics and the system dynamics. Suppose we'd like to model that. And one way of doing that would be that we introduce bath fluctuation, the fluctuations in the energy level of the bath, which are like stochastic Gaussian white noise processes. So basically, every energy level, they are fluctuating about some zero mean value, and it is delta correlated with a variance kappa square. So, I mean, if we look at the whole Hamiltonian, we have system, and in environment, it's a defining static Hamiltonian. We may have a drive on the system. We might have interaction between the system and environment, and also between, if it is a multipartite system, then within systems, we can have dipolar Hamiltonian. So all these, we club them together, call it H effective. And also we have this fluctuating Hamiltonian that you see here. And then to derive it, we start from von Neumann-Liouville equation that the rate of change of rho is equal to the H effective plus HL. We are in the interaction representation. So the static Hamiltonian of system and environment, they do not show up. And then we integrate it over a coarse graining time interval. We choose a time interval delta t, which is intermediate between the fluctuation time scale and the system dynamics time scale. And we also take the partial trace over the environment. When we do that, the left-hand side is straightforward. We have reduced density matrix of the system at time t and time t plus delta t. And the right-hand side, we have a commutator between H effective and the rho at an intermediate time that can be evolved using a propagator. This propagator follows from Schrodinger equation, H effective and HL. And we integrate this Schrodinger equation using Neumann's scheme. So identity minus H effective U and HL U. And we make an unsearch here that all preceding evolutions are due to the fluctuation. So that means we can replace this U by UL. We do this because this expression is already linear in H effective. And we would like to linearize the system Hamiltonian. Now, the first and third term now can be clubbed together because this U is UL. So identity minus HL UL gives us UL T2 T1, and we have H effective UL. So this propagator is a hybrid propagator. We have finite evolution due to the fluctuation, and we have linearized evolution due to the system Hamiltonian. And then what we do is we plug it in this propagator in the integrated form, and we do perform ensemble average. We assume the Markov approximation, which is essentially the correlations decay pretty fast with an exponential dependence characteristic time tau c, and the Born approximation that initially the system and the bath are separable. And the left-hand side, if we use a coarse graining description, then we arrive at a quantum master equation. The rate of change of density matrix is given by, in the first order, drive, and also in the second order, there could be drive or system bath coupling and all Hamiltonian. So this is our prescription. This is our quantum master equation, and we are planning to use that. I took rather long time to introduce it because it's very important that we understand the fluctuations playing a big role in providing what we call a regulator. And in the dissipator, the second term, double commutator, we can have drive and the system bus coupling. In the first order, we typically have the drive. And once we do that, the quantum master equation in the Liouville space, we have already seen its matrix form. Now it looks slightly more elaborate. We have omega 1 square tau c by 2, this particular term in the diagonal and in the off-diagonal, anti-diagonal term. These are the drive-induced dissipation. So drive is causing a kind of dissipation. But then how does the block equation look like now? It looks like the standard block equation that we had before, but with some extra term. We have extra dissipation coming from the drive in the equation of x, y, and z, and we also have some shift term. Both this, the decay term, which is proportional to the square of the drive, after all, it's a second order contribution. Those were verified experimentally. And the way the experiment was done is that we try to do a notation experiment. And in the notation experiment, when we try to do it on a sample, we have different drive frequency at different places. It's an experimental reality that you cannot have a perfect drive amplitude all over the place. So, which means that you can have a first order dephasing because the different part of the sample has different notation frequency. So we refocus that using a theta minus theta scheme, that you first apply a theta pulse, then apply a minus theta pulse to bring it back. And then when they evolve, the decay is purely due to the second order effect. There is no first order decay. So we expand the experimental scheme, make it a little more sophisticated. And what we see here, the important result is here, that in the x-axis, we have the Rabi frequency, and the y-axis, the dissipation rate coming from the drive. The dissipation rate of the Z magnetization. What we see is a clear parabolic dependence, which establishes the legitimacy of the term that we derived, that the drive contributes to the dissipation at the second order. And we also checked its temperature dependence, and we found the bath correlation time goes down at higher temperature, exactly as it is expected. Now we apply this on quantum information. I am coming to the main part of the talk. The first application that we did on this quantum master equation is on the efficiency of quantum information processing. What we do is, very simply speaking, is this: because any real system which is connected to environment, they decay, you need to perform the quantum gates, you need to perform the computation part as fast as possible, which means you apply very short quantum gate. And shorter quantum gate means stronger drive amplitude. And strong drive amplitude means you have drive-induced dissipation, which means you introduce additional decay, so your fidelity goes down. Whatever you would like to calculate, suppose we are applying a simple Hadamard gate. And the Hadamard gate is supposed to give us a simple, starting from, say, state 0, it is supposed to give us a linear superposition between 0 and 1. But the fidelity of the gate goes down if we try to apply a stronger drive because of the drive-induced dissipation. And slower drives are also not good, because if the drive is too slow, the system environment coupling causes a dissipation of the coherence. So which means you have to have an optimal drive speed, drive amplitude, which gives you maximum gate fidelity. So what you see here, we are plotting gate fidelity. The yellow color gives us the highest fidelity, and the darker colors are low fidelity. And as you change the drive amplitude in the x-axis, you see for lower drive amplitude and higher drive amplitude, the fidelity goes down. And also, this is the environmental correlation time. A shorter correlation time is preferable. A larger correlation time is not good. So this basically gives us an idea that you have to have an optimal drive amplitude. But drive amplitude dictates the Rabi frequency. So Rabi frequency dictates the clock speed of quantum information processing. So which means the quantum information processing as such on a real system should have an optimal clock speed. So this was our earlier work, an example of FAQME, the work done by my PhD student Nilanjana Chandu, and she also worked on this today's topic, that emergence of Born rule. So let's look at the dynamics of open quantum system as described by our master equation. So what we consider is a strongly driven system which is weakly coupled to its environment. And our master equation can handle strong drive as long as time scale separation is respected. And suppose now you would like to measure an observable on a quantum system. You prepare a drive using that observable. Okay, drive means the external perturbation. So whatever observable you would like to measure, you prepare you make the drive. Say, for example, you would like to measure sigma x, then your drive will look like omega times sigma x. Omega is the amplitude of the drive. Now, our master equation now looks like this, that rate of change of density matrix. We have the drive in the first order. We have a drive-induced dissipation, the dissipator that I showed earlier. And we have another dissipator coming from system environment coupling. Let us suppose that we are applying a strong drive. By strong, I mean the dissipator coming from system environment coupling is much weaker than the dissipator from the drive. So which means that these two terms, the first order drive and the drive-induced dissipation, they will take the system to a quasi-steady state, meaning system starts an observable. Here we plot a schematic schema of an observable, expectation value of an observable. It starts from some initial value, and then as a result of the first two terms, it quickly goes into some quasi-steady state, region 2. And eventually from region 2, the system environment coupling will take it to the final thermal state. And our focus at the moment is to look at the region 2. What happens? I mean, how does the density matrix look like at this stage? So what we do, we write down the equation once more, but this time we do not include the system environment coupling because we are stopping the dynamics in region 2. The equation looks like this. The rate of change of density matrix is given by the first order commutator, and we have a double commutator, which is the second order contribution, and the prefactor is coming from the environmental correlation time. And we work in the eigenbasis of the drive. So which means the Hs is essentially diagonal. We write it in this form, omega, and then lambda I, phi I, phi I. And the density matrix, initial density matrix in this basis could be having diagonal as well as off diagonal forms. And then we let it evolve using this equation. So we have, this is the Hamiltonian, which is essentially diagonal. And if we let it evolve, what we see is any term in the density matrix, like here A12 or A13, in general, the AJK, it evolves with the dissipator eta jk and an oscillation. The dissipator, the dissipation coefficient, it is proportional to the square of the difference of the Lerner frequency, I mean the eigenvalue. So which means the diagonal terms do not decay at all, and all of diagonal terms, they decay. And so that means if you start from a density matrix of this nature and you let it evolve, then in the region 2, here in the previous slide, when the system has reached a kind of steady state, you do not have the off-diagonal terms anymore. But this is exactly what is predicted by the Born rule. So which means that if you take a system, apply a drive, then this drive, application of the drive is like an act of measurement of that particular observable, and that gives you a final steady state exactly compatible with the Born rule prediction. Again, we take the example. I mean, this looks like a theoretical schematic sketch. If we take a particular example, it might be clearer in this case. So what we do is, here is our initial state prepared at some arbitrary point on the Bloch sphere. It's a generic description between 0 and 1. and would like to measure sigma y on this stage, on this system. So which means we apply a drive, which is omega, the drive amplitude, times sigma y by 2. And this sigma y has non-degenerate eigenvalue 1 minus 1, and we already know their eigenvectors 0 plus I 1 and 0 minus I 1. And the initial state, whatever we prepared here, we can also project it. I mean, we can write it into in the eigenbasis of the observable eigenstates. And in our case, the C1 and C2, if we calculate, if we look at their mod values, mod C1 square and mod C2 square, this should be C2 square. Then we have 1 plus minus sine theta sine phi by 2. These probabilities what we should have if we follow the Born rule. Now our dynamical equation in the eigenbasis of the drive, it looks very simple. The density matrix column vector, remember this is not in the 0, 1 basis, this is in the drive basis. There, the coefficient matrix has the two dissipative term minus omega squared tau c for rho 1, 2 and rho 2, 1. These are the coherences, they vanish. So which means the rho 1, 1 and rho 2, 2, they will remain exactly as they were. So here we have the density matrix. This is again, we have come back to the 0, 1 basis, and this is as a function of time. So we see the coherences, they have exponentially decaying time dependence along with an oscillating part. So net result is, after a long time, this coherent part essentially vanishes when this time is long enough. From an experimental perspective, these are practically 0. And eventually what you get is a state which is exactly as predicted by Born rule. So this is again Nilanjana's work. We did it in 2021. It retrieves the Born rule. Now, I showed only a simple case, but it works for multi-qubit system. It works for degenerate case, which of course, I mean, we are not giving any example here except the statement. Okay. Now, one thing we did not discuss, I mean, like what happens when the system environment coupling is finite. When the system environment coupling is 0, then essentially the dynamic starts in region 1 and it settles down in region 2. So that means on the Bloch sphere, suppose you start from this green sphere, the green point, and in the region 2, after your dynamics is over, you end up at 2 equatorial position. Those are the 2 eigenstates for sigma y. Okay. This is where we enter. But this is only part of the picture because we still need to add the system environment coupling, its contribution. That we are planning to do that now, so that we have a complete description, not an asymptotic behavior. So this is what we do. We include the system environment coupling. We know that it provides relaxation. We already studied that. I mean, we have seen that when we were looking at the Bloch equation. And the drive provides the drive-induced dissipation. And as before, we are assuming the drive-induced dissipation is much stronger than the relaxation. And observable is sigma y. And if we do that, then in the Born rule regime, only sigma y survives. Okay, let me explain that statement. We go back here. So this is our density matrix in the eigenbasis of the observable. Now suppose the observable is sigma y, then the density matrix will be diagonal. But suppose the density matrix is a mixture of sigma y and sigma x. So sigma x will be in the off-diagonal part, sigma y will be in the diagonal. The Hamiltonian, the drive is essentially diagonal, which is sigma y. So if you look at this equation, when density matrix is exactly sigma y, it will commute with the drive and it will survive. It will not evolve. But all other Hamiltonian, like sigma x or sigma z component, they will dissipate because of the drive-induced dissipation. So what we expect here that when we have finite system environment coupling, and we start with a density matrix, which is partly sigma y and partly sigma x, the sigma x part will dissipate, sigma y part will survive. But this is before the relaxation takes over. The final steady state will be dominated by relaxation. Now, how does that work? I mean, what happens then? Okay, so here are certain simulations, like we start from an initial state, which is an eigenvector of sigma x and eigenvector of sigma y. So, I mean, initially, if we try to calculate the expectation value of sigma x and sigma y, we will have non-zero values, both of them. And then we have chosen other parameters, which are part of our master equation, the T1 value, T2 value, and the amplitude of the drive, the system environment coupling, and the equilibrium polarization. These values mostly motivated from the magnetic resonance, NMR. In NMR, these numbers are quite common. Okay. Now, suppose this is actually the time evolution of the magnetization using only the relaxation part. There is no drive. So which means initially the orange line tells us that initially we had some Y magnetization and eventually it vanished. And we also had X magnetization, that too vanished. And it is the Z magnetization which kind of went to the final steady state. So we have equilibrium polarization exactly equal to 0.6. This is M naught value. This is what we expect according to our quantum master equation. If we apply drives, then as I said before, the sigma y part, that means My, will not evolve at all. It will stay undisturbed, and the X and Z part will decay and will vanish. This is exactly as we expect. I mean, if we do not have any relaxation. So both are well-studied behavior. And what we have when we add both, we have initially the drive-induced dissipation causes the vanishing of My, Mx, and Mz. So this regime where the sigma y survives and nearly flat, this is like what is predicted by Born rule. And after that, the relaxation takes over. It takes sigma y and to 0. So what you have here is the steady state solution of modified Bloch equation. So this Born rule regime is basically a finite area, and its existence, it owes its origin to the difference in the time scale between the drive and the system Buck coupling. I mean, the two dissipator must have different time scale. The drive-induced dissipation, it acts much faster, it's much stronger than the system Buck coupling. And here what you see is the fidelity plot to better analyze. We are calculating the fidelity between the state predicted by Born rule and state that we have. So this is a time, this is as a function of time. So we are calculating fidelity as a function of time. The system is evolving. When it enters the Born rule regime that you see here, then the fidelity is highest, almost 1. So that means at this particular stage, the density matrix behaves as predicted by the Born rule. But before that and afterwards, it is not same as the Born rule prediction. This is like a thermal behavior, and this is the dynamics has not settled into any of the steady state yet. So this is how the fidelity behaves. So we have a regime when the Born rule is kind of Born rule emerges dynamically. And now here we show you the contour plot. This is function of time in the x-axis, and in the y-axis we have omega-1, the drive amplitude. So what we see is when the drive amplitude is strong, the yellow regime, the triangular region, it tells us that we have good fidelity. We have the existence of a Born rule regime. But with a too small drive, the system Buck coupling is too strong, which means that this dissipation starts acting earlier or you can say this DID with a very weak dive starts acting later, which means the separation vanishes and we do not have any Born rule regime. So, I mean, if we have to have a Born rule like behavior in a realistic system, we have to apply a minimum drive amplitude. And this is flat. This is flat because this decay is coming from the system environment coupling. And here the system environment coupling is essentially fixed. So it always vanishes at a particular time. But if the drive is strong, then what happens is the DID is stronger, and this particular regime where the transients vanish, it shifts left towards left, and we have a bigger Born rule regime. And here we study what we call temperature. See, the bath correlation time, it is expected to be inversely proportional to temperature, in the sense we can always set KBT equal to H by tau C, and that will give us some dependence of the fluctuation correlation time on the temperature. So what we see here, it does not change the Born rule regime, except it shifts the whole thing. And tau C, the left side of the edge, the emergence of Born rule, that is that depends on a time scale given by omega 1 square tau C. So it is linear in tau C, and its vanishing depends on system environment coupling squared times tau C. So with both the numbers unchanged, as we change tau C, it linearly shifts. So no surprise there. I mean, like this is what we expect. So I mean, I'm nearly done. I'm done essentially. So I'll summarize. So measurement, if we try to mimic a measurement, then we can use the observable that we would like to measure as a drive. Then the act of measurement can be described by using a fluctuation-regulated quantum master equation, our master equation. Okay, that provides drive-induced dissipation. This drive-induced dissipation destroys the unwanted coherences, and it also works for non-degenerate cases. And one more assumption is the source of the drive, that it should be strong enough not to be perturbed by the system. So there is no feedback. It's not like if we apply a strong drive, the system is changing back. If we have such a behavior, then we may have to use a non-Markovian formulation of the master equation. And so strong drive is application of a strong drive is like an act of measurement, and that gives us Born rule as an asymptotic behavior. And when we add system environment coupling, the Born rule behavior is only for a finite duration. Eventual state is a final steady state, very different from Born rule regime. And the separation of time scale is crucial. We have to have strong DID and weak relaxation. And we need a critical value of omega 1. Below that, the Born rule regime does not appear. We have NMR-like passive measurement. In magnetic resonance, oftentimes, the measurement does not involve any obvious collapse. Okay, but we are still investigating that. And the temperature changes the Born rule segment. I mean, temperature changes shift the Born rule segment. It does not destroy it. And this is, so basically we showed that it is our master equation. It helps explain the emergence of a Born rule in a realistic setting, realistic in the sense that all quantum systems are essentially open quantum system. So it is expected that we have to use an open quantum system formalism. And what we see is we very efficiently show that a Born rule like behavior emerges dynamically. Our approach is very different from other approaches, and that's it. This work is from our lab. This is our lab in IISER Kolkata, spin lab, and at IISER Kolkata. Thank you very much.
Yeah, thank you, Professor Bhattacharya. So, yeah, I open the floor to students or other attendees. Like, if you have any question, please come forward. Okay, I'll just wait for some more time.
Sure.
Yeah, are there any questions? I can't see any. Yeah, hi Ranjeet, please go ahead.
Yes, right. Thank you for your talk. I have two questions. So what type of dissipation mechanisms you used in system environment coupling?
Okay. In this particular case, we did not introduce any particular one because the system environment coupling can be modeled by many different ways. The most common one is we often assume a Jins-Cummins type Hamiltonian. So environment can be modeled as a collection of harmonic oscillators. This collection could be finite or infinite. Traditional quantum master equation, they assume an infinite collection of harmonic oscillators. And system is connected to the coupled to each harmonic oscillator using a Jins-Cummins type coupling. But this is not important in our case. Why is it not? Because the effect of that particular coupling, system environment coupling, and number of Bath harmonic oscillator, if you take the trace over the Bath coordinate, eventually what you get is a single number, a T1 or T2, two numbers which describe how fast the system go back to equilibrium, the populations restore to equilibrium, and how fast the coherences decay. So these two numbers are eventually end product of the system environment coupling and the entire formalism. And because our focus was mostly on drive-induced dissipation, so we just took the T1 and T2 to be two parameters here, like I showed some 100 seconds or so. So that, I mean, I hope that answers your question.
Thank you. Second one is when one calculates fidelity,
Yes.
then there are two states. One is the target, and the second, the state which is compared with the target. So in your case, could you please show the target state?
The target state is this. I mean, I have not shown it here, but it is straightforward. I'll tell you how to do that. Okay. So look at the initial state. Initial state is 0 plus I1. This is the eigenstate of sigma y, and this is an eigenstate of sigma x. All we have to do is to take this state, normalize it, and rewrite it in terms of phi plus and phi minus. Phi plus and phi minus are the eigenstates of sigma y. Okay. Then the target state would be, target density matrix would be like mod C1 square, phi plus, and mod C2 square, phi minus, phi minus. So this C plus and they are calculated this way. This psi is the initial state, and this phi 1 and phi 2, these are the states of sigma y. So what you do is you calculate mod C1 square and mod C2 square, and your target density matrix is mod C1 square and mod C2 square in the diagonal. Of diagonal terms are 0. This is your target density matrix. And as you evolve with time, of course, I mean, you have a different density matrix, which exactly matches with the target for finite duration. Okay. I mean, I'm sorry that I did not show it, but this is how you calculate it. Okay.
Thank you.
Okay.
So are there any other questions? Yeah, so Professor Bhattacharya, I had a couple of questions. Like, can you hear me?
Yeah, I can hear you.
Yeah, so first is, can these systems be extended, or a similar analysis be extended to a spin cavity system where you have a strong coupling, or?
Okay, so
or
you
is
were
this
wondering,
essentially is this
you-
essentially a feature of semi-classical interactions, or can you also go to the complete quantum interaction and still study it?
okay, okay, I understand. See, I mean, one trouble with the atom cavity interaction is this is fixed. You cannot, I mean, you can use this analysis. We are already working on it, that one atom or multiple atom in a cavity But the focal point of this particular study is how bond rule emerges, which means the bond rule emerges means essentially you are trying to model the measurement. Now, in an atom cavity interaction, of course, that coupling cannot be tinkered, while during the measurement you can choose to observe one observable or the second observable. So it is slightly difficult for the atom cavity system because the coupling Hamiltonian is not, you cannot tinker that very easily. I mean, that is what I understand.
But if you can engineer the coupling in some
then
sense.
of course, then you can use this method, and you will see that as the atom, as a two-level system coupled to the cavity, as it evolves with time, there would be a period when the density matrix of the system will be given by exactly the bond rule.
Okay.
For a finite duration. Yes.
Yeah, and the second question I
that's-
had is, yeah, I hope it's not silly, but would it act differently whether you take Markovian noise to model the environment or whether it's non-Markovian?
Yes, I mean, that is what we feel, that in this case it is Markovian, and when it is Markovian, I mean, I would like to go back to the complete form of our master equation. Here it is. In the right hand side, the dissipator that you are looking at, it has upper limit infinity, lower limit 0. I mean, when we started deriving the our master equation, we had an integral from t to t plus delta t. The t in the upper and lower limit vanished because of a change of variable. That came from the stationary nature of this two Hamiltonian, and also the delta t that can be replaced by infinity as long as the system is Markovian. That means this integrand vanishes long before delta t. So which means the tau c must be much shorter than delta t. If it is non-Markovian, we cannot make that assumption. So this coarse graining approach will give us a very cumbersome form where at which time scale we observe the system, that will kind of show up in the equation, this is very disturbing. So that means you will have a situation where how fast you are observing the system, the behavior of the system will depend on that. Okay, so this definitely will affect the bond rule dynamics. There are two ways. This is one way. The other is, of course, the past time dependence will show up. So overall, we have not tried that, but this is very interesting point that you are raising here, that we believe that the bond rule regime might see additional modulation. It won't be exactly the same as the Markovian.
Because notice there are a lot of studies on engineered environments, and I was just wondering, like, if you can engineer an environment and push it to some optimal behavior or something like that.
Yeah, that can be done. This is already being done by certain groups, where what they do is they take a drive, and the drive amplitude and the phase they generate using random numbers. Essentially, the system fills a random field which feels like it's coming from the bots. So engineered noise is playing a big role. Yes, I mean, it's being investigated very actively. Yes.
Okay, so thank you so much, Professor Bhattacharya, for this very interesting talk. And yeah, so with that, I'll go to the next invited talk by.